So I'm guessing you might have some questions on number 6.
And 3.
Okay?
Yes.
3 is easy.
Let's just talk about number 6.
Oh, shut up. It was not easy.
So this is going to be relative to the lab that you're going to do today. So all this is a different way to calculate the centripetal force. So basically, you've got this rubber stopper swinging around over the top of your head, like this. Now, there's 2 ways that you can get how fast that rubber stopper is moving. What you're going to do today is that you're going to measure the radius, and then you're going to measure how long it takes for it to make 1 revolution, and you're going to go, oh, V equals 2 pi r over t. Here's going to be the circumference. That's how far it travels. This is how long it takes to make 1 revolution. Divide that, boom, there's your velocity. Easy, boom. Okay, that's just one option. If you know the radius and you know the time. But you're sitting there going, wow, I'm a physicist. We throw stuff. Okay, so let's get it going around, and we're just going to throw this thing. So when we're swinging around, we let go of it. Okay, and so from the side view, here is this rubber stopper coming around. You let go of it, it becomes a projectile. Now, because you're in a horizontal plane, what's your initial vertical velocity? 0. So Vy naught is going to equal 0. So it's basically a lemming problem. Do you know how far it is above the ground? Yeah. What's the only thing, if Vy naught is 0, what's the only thing that determines how long it's in the air? 2 things.
The mass and gravity.
No.
If you say that one more time.
The height and? No. Vy naught 0. Height and your gravitational acceleration. Right? So you can look at this and go, oh, right. X equals 1/2 at squared plus v naught time. My initial vertical velocity is 0. You know your gravitational acceleration. You know how far it falls. Figure out how long it's in the air. Okay, and that should be less than a second. So then, you know, okay, well, it's in the air this distance. We can measure how far it travels, right? Because, okay, well, I'm here. I know the point that I let go of it. I know how far it travels. So then you can go, oh, range equals Vx time. You know the time, you know the range, you find your Vx. So that had to be the speed that it had when it was traveling around. Now, today in the lab, we're not going to use this, okay? Mainly because of the fact that I really don't want 6 groups of rubber stoppers flying around my room. And then you've got to have somebody watching where it lands, and it's cool, but it's really just not a practical way to determine the velocity. You can do it that way. I just don't want a room full of you doing it that way, because somebody's going to lose an eye, and it's not going to be good. So anyway, so if all goes well, your tension, which is the centripetal force, it's the same thing, should be something around your current age.
So the time should be under half a second?
No, it said the time should be less than a second.
Okay.
Now, some of you have like completely spaced off this whole thing of significant digits. So when you're finding that value of time, keep more digits than what you're going to need later on. Okay? Because some of you are going to get this and you're going to round it to 0.8. Okay? You're only going to have 1 significant digit. When you're doing these sub-calculations, put in more digits than you're going to need and then round them at the end. Every number I have given you on this assignment has at least 3 significant digits, which means every answer that you have should have at least 3 significant digits. Yes?
Okay, so what do we do if it's like 124.1?
It's 124.
It's, you just don't worry about the 1, man.
No, because then you have 4 significant digits.
Yeah, that was...
Now, if it was where it gets weird, if it was exact, say it was 100.1, then you want 3 significant digits. Okay? So one option is that you just leave the decimal place here, which makes it 3 significant digits. You could go old school and put a line over the top of it and that makes them significant. Or you can write it as 1.00 times 10 to the second. Okay. Now, on number 3, here's the idea on number 3. So, you've got this car driving around on a flat track. Okay, so here's the car.
That's talent.
Okay.
That's a really good car.
I would have drove.
We can flame it.
Oh, yeah.
Okay.
You have to get red.
See, we did the same thing.
There, that.
Oh, yeah.
Years of sitting through boring physics lectures, okay? I'm telling you.
Hey, I drew an elephant one day.
Okay, good. All right, so here's this deal. This car is going to be making this turn. First off, what's allowing the car to turn? Now, here's what I don't want you to say. Centripetal force, okay? Centripetal force, we call it centripetal force, but centripetal force only exists because something else is there. There's a rope, there's gravity, there's friction, okay? Somebody on the outside physically pushing it in, which doesn't make sense on a car, but that's another option. So some external force has to be applied. Centripetal force is not a fundamental force because it only exists because of something else. Okay, so here's the deal. Draw the forces acting on the car. Okay, I got gravity. I've got my normal force. Now, there's also centripetal force because this car is moving in a circle. What's the direction of the centripetal force? There's 2 parts to your answer. Kendra, what's one of them? What's the direction of the centripetal force?
It's inward
Inward, beautiful, and
at a right angle with
to the
velocity vector.
beautiful. Because this car wants to go in a straight line. Okay? So, this is the direction of my centripetal force. Well, what's creating the centripetal force? One thing and only one thing. Friction. So you look at mu equaling force friction over force normal. You know what the coefficient of friction is, 1.05. That is an absolute best case scenario. Absolute best case scenario. You can find your force normal because you're on a flat surface. Okay, that's cool. That's mg. So if you can find the frictional force, that's the same as your centripetal force, and centripetal force is mv squared over r.
It's what?
Gas freeze.
mv squared over r. So at this point, you know the centripetal force, you know the mass, you know the radius, the only thing you don't know is the velocity. So if all goes well, yes, in being mass, just as it's
Your
always
first
been.
teenage birthday.
On number 3?
Velocity?
Yeah.
Yeah.
Yeah, I thought you were talking about the force, and I'm going, whoa, that's bad.
Wait, whoa.
Wait, what?
So
On number 3, the velocity should be around your first teenage birthday.
So 13.
Hey, just because you're wearing a football thing doesn't mean you have to answer
That
it
is
like,
around.
what's your number, 13? Oh no, 31. No.
So is that the wrong?
I wear helmet and shoulder pads.
That is around a 25.
I have gained brammage. Sorry. Okay. Anything else? Make sure, and listen to me, make sure on that whole problem on number 1 that every answer you have has 3 significant digits. Okay? Now, if you only have like 0.4, let's say you just have 0.4 as an answer, don't randomly chuck zeros on the end of it. Okay? You probably round it. Okay? So if just because you have 0.4, don't go, oh, just chuck zeros on the end of it. You can't do that unless those are actually zeros. Okay? Oh, and by the way, some of your answers should involve a 4 on that front side. Not all of them, but some of them should involve 4s. And some should involve 2s. Anyway, anything else? Go on to my soul.
Yeah.
So this video doesn't take very long. But this is like the classic demonstration of what happens when you have centripetal force and then when you lose centripetal force. Now, here's what I never want you to say. Okay, well, there's any number of things I don't want you to say, like, hey, pass me the heroin. That ranks right up there. But,
The what?
I'm just saying.
What's another name for heroin?
So, yeah,
Heroin.
man.
Oh,
So
I thought
anyway,
you said heroin.
here's what I don't want you to say. Oh, inertia overcame the frictional force. Okay? Bad. Inertia is not a force. What you can say is that you lost the frictional force that created the centripetal force, and therefore inertia had you go in a straight line. But you cannot say, oh, inertia is greater than a force. Okay? No, it doesn't work. That's like saying, you know, a sheep is different than a mountain, which it is, but you're comparing two completely different things. So basically what's going to happen here is that they're going along, they have centripetal force created by friction, they lose the frictional force, and then bad things happen. So,
Did you say this was long or short?
no, it doesn't take very long.
Throttle with a sudden burst of speed. He tries to pass another rider, but the racer's daring move leads to disaster. Killer whites out.
Okay. So at this point, look at what happened. So he blew an oil line. So the surface basically became frictionless at that point. So he was going along in a curved path. Lost the friction, and he wasn't like tied to a rope, or there wasn't like a gravitational source here to put him into orbit. So inertia takes over. Watch the path of all, because there's going to be a series of these. Watch the path of them. As soon as they lose that frictional force, it isn't like we showed yesterday, you know, where they kind of, oh, they curve a little bit. No, they go in a straight line at a constant speed until an outside force acts upon them, which in this case is this barrier.
He looks like he's about to break his neck.
The bike topples over.
Inertia kicks in
It careens across the track.
in a straight line.
Hits a wall. And then
Whoa!
is barely decapitated.
Seriously, I mean, that
The
much.
trouble starts here. Younger's hitting speeds of 205 miles an hour. He guns it.
That's fast.
Smoke
That
billows.
does not look like 205.
His oil line ruptures
This is just what they said.
and spreads a slick on the track. Younger's in a violent skid across the asphalt.
Notice he is going in a straight line.
He slams into a barrier.
Watch his neck.
Oh.
Then cheats death by only an inch.
Oh, it went over him.
Yeah.
I thought it went to the side.
Now, how'd you like to be the guy holding the camera?
Why would you?
How about no?
Why do that
Hits a
sport?
giant wall with such force it bounces him back to the ground. A lucky break that saves his life. Other riders hit the oil and wipe out.
Yeah, so it's just one series after another. Boom, boom, boom.
In all, 7 racers slide into the trap. And no one is seriously injured.
Okay. So that's like the classic example of what happens
What is he
when
seriously
you
injured?
lose that frictional force. You just go in a straight line, boom, there you go. Okay, so stop that, I gotta get. So here's what's gonna happen with this lab. So this has become affectionately known as the cowboy lab / cowgirl lab, depending upon your preference. And here's the basic idea. So we're going to look at the variables that deal with centripetal force. And the biggest one we're going to look at is this equation that centripetal force equals mv squared over r. So basically we can control three different variables. We can control centripetal force, we can control mass, and that's going to be the mass of what's being swung around on the end, okay? That's going to be important. And then we have the radius. So those are the three variables that we're going to control. So basically, on trials 1 through 4, I tell you specifically which masses to use. On trials 5 through 8, we're going to change the radius. In trials 9 through 12, we're going to change the mass of the stopper. Okay? So 4 different trials, 4 different variables that we're going to manipulate. Now, the rule is you can only change one at a time because otherwise you're changing 2 things and that just gets weird. So here's the basic technique. You can take a piece of thread and feed that through a glass tube. Then that's what you're going to hold on to. So then you're going to hold it like this. This is why it's known as the cowboy lab. And you're going to get that swinging, okay? And if you hit just the right velocity, then the mass will hover. And if you go a little bit faster, you can change the radius, okay? And then if you slow it down, it's magic, okay? All right? So here's going to be the whole point of this.
It's pretty nifty.
It is pretty nifty. So here's the whole point of this, is that what we're going to assume initially is that whatever the gravitational pull is on this weight hanging down, that's going to be the centripetal force. Because something has to be providing that inward force. And so what we're going to do is once you get that moving, then you're going to say, okay, whatever the gravity is pulling down, that's what's creating the centripetal force. So you're going to be dealing with 2 different masses. This 200 gram mass, like in this case, and then the mass of the stopper. So you have to keep track of what you're changing and what you're holding constant. So when you look at what you're going to do, over here on this first column, okay, trials 1 through 4, I tell you specifically which ones to use. So what you're going to do to get the mass of the stopper, pretty easy, take it, set it on the scale, get a reading, boom, there you go, mass of the stopper. That scale is going to be measuring in grams. Everybody knows how to convert from grams to kilograms. If you're not, ask me. Now, what you want to do is you want to time 10 swings, okay? You want to time 10 swings. So what you want to do is get this thing going, okay? And then once you get that thing leveled out, and by the way, you want to make sure that this is in a horizontal plane. You don't want this action going, okay? You want this thing in a nice horizontal plane, like this. So you got this action going. So once it gets going, then you want to have at least 2 people counting. Now, if this lab goes south, and as odd as this sounds, and I'm not insulting anyone's intelligence, if this lab goes south in terms of the data, it's because you can't count to 10. Okay? No, it's true story. Mainly because some of these are going to be going so fast it's hard to count. So when you do this, and you want to have 2 people timing this deal, if you're off by like a lot, like 0.3 seconds, 0.4 seconds, don't just say, oh, we'll take the average.
We're up by.
If you're, yeah, you guys were screwed. You might want to buy data from another group. I'm just saying. It'd be worth
I'll
it.
just run 2 stopwatches.
Okay. So, but you want 2 independent people doing this counting. Okay? Now, here's a couple of things about lab protocol. We all know you can count to 10. Don't count out loud. Okay? So in other words, other groups are going to want to beat you if you're doing this. 1, 2, 3. Okay, bad. Okay? Now, if you get bored in this lab, this is one of the funniest labs to watch other groups because usually the people that are swinging aren't necessarily cool when they're doing this. Okay? They're usually doing this. Okay? Or watch their offhand. So they'll be like the Statue of Liberty. Like if they move the hand, it's going to screw things up. And then you have the people that are counting because they're doing this. Okay? So if you, I'm just saying, if you get bored, kind of get a look around,
Damn, you alright, man?
you might see some interesting facial expressions. Okay. So that's the data that you're going to have. So on those first 4 trials, you're going to go from point 1 to point 2 to point 3 to point 4. So let's make sure that we get this right. So you got a 0.2 kilogram mass. 0.2 times 9.8 is?
19.6.
How about 1.96?
1.96.
Okay. So over here on the column, where you've got the 0.2 kilogram mass, go across, your centripetal force would be 1.96 newtons. So whatever column, whatever that mass is here, multiply that by G, there's your centripetal force column. Let me give you a word of advice on the first 4 set of trials. The hardest one to do is the 0.4 kilogram mass, because that's the one that has to be going the fastest. So start with, even though it's listed, you're going from point 1 to point 2 to point 3 to point 4, actually start with the 0.4 kilogram mass, because if you can do that one, then all the other ones will be easier to do. Because what I don't want you to do, because you're going to pick whatever radius and whatever mass of stopper that you want. What I don't want you to do is you've done the first 3 trials and you're cool, and then you hit that 4th trial and you realize there's no way we can count this, and then you're screwed. So start with the 0.4 kilograms. If you can get that to work, then the other ones will be easier to do. So let's talk radius. So as this thing is going around, okay, swinging it over your head, right? You need to measure a radius. Well, it's going to be a little bit tough to do when it's swinging around. Someone's going to get, you know, like an eye taken out. Bad. So what you want to do is measure your radius, like take out a meter stick, lay out the radius, measure from the center of the stopper to the edge of the string, or to the edge of the tube. Then the easiest thing to do is, and I've got different colored markers back there, is to make a mark on the bottom side of the string. So that way, you know, you've got a mark here, and then you can watch it, and then when that mark gets to a certain point, then you know you're at that particular radius. Okay? Got that. So that's just the easiest way to do it. Boom, home run deal. Got that. So you get the mass of the stopper, you're going to change the centripetal force, because you're going to be changing the weight. So now, let's talk big picture. So let's look at this equation. So on trials 1 through 4, what's happening to the centripetal force? Getting bigger, getting smaller? It's getting bigger. So this side of the equation is getting bigger. This is the mass of the stopper. What's happening to the mass of the stopper? What's happening to the mass of the stopper?
Remaining constant.
It's the same, okay? Because you're always going to have, you don't want to change 2 variables. I don't want to change the centripetal force and the mass of the stopper at the same time. So the mass of the stopper is a constant. What about the radius? It's a constant. So what you could do is look at this mathematically. So this ratio of mass of the stopper to radius is a fixed value for the first 4 trials. It's not going to change. I don't care. It's a number. I don't know what the number is. I don't care what the number is. It's just going to be a number. It's going to be a constant. So if you want to, you could look at this and go, well, if I view it that way, then this equation is basically centripetal force equals kV squared. Okay? Here's a constant, because it's the same ratio of mass to radius.
What's K?
It's just a constant. Now, just like if you're in a math class, if you're in a math class and I said, hey, let's graph this. Y equals kx squared.
Yeah, we are.
Huh?
I got it.
So,
We got to solve it.
no. If I just said you're in a math class and graph this, roughly what's this thing going to look like?
It's going to look like a parabola.
A parabola, right? It's going to look something like this. True? So what you're going to do, you're going to end up drawing 3 different graphs.
Oh, God. I thought we're past that.
Oh no. Oh no.
I don't see any graphic.
What?
Just kidding, I got some mistakes.
Oh,
I just wanted to.
I don't think I have paper to be honest.
Kid, are you?
Oh, I know.
Okay. So guess what you're going to graph on the y-axis?
The independent
variable.
Otherwise, in this case, it's going to be centripetal force. You're going to graph velocity. You're going to graph velocity on the x-axis, and it should look something like this. Okay, when you get done. Now, 2 of the graphs will start at 0, 0, and I explicitly tell you, hey, these are going to start at 0, 0. The third graph won't start at 0, 0. Just saying. All right. So,
Thanks for the hint.
not a problem. So, when you get this data, okay, you're going to draw this graph, boom, plot it out, there you go. Now, on trials 5 through 8, you're going to change the radius. Now, when I say change the radius, I mean change the radius. In other words, I don't want you to go from 0.5 meters to 0.51 meters to 0.52 meters. I want at least 10 to 15 centimeters of change within that radius. Okay? So again, trust me on this one. The hardest one to do with this radius is going to be with the one that's smallest. Okay? Now, let's look at this. And again, in terms of the big picture. So if you go back to this equation, when you look at trials 5 through 8, are you going to change the centripetal force? No, you're going to keep that constant. So pick one, 0.2, 0.3, 0.4, I don't care. Pick one of those values and you're going to keep that the same. You're going to keep the same mass of the stopper. That's going to stay the same. Okay? So that won't change. But let's say you're looking at making the radius bigger. So think this through. I want to produce the same value over here. I'm not changing the mass of the stopper. That's a fixed value. So as the radius gets bigger,
Swing it faster.
what has to happen to the velocity?
Increase.
It has to increase. Okay? It has to increase. Is it going to increase at the same rate? No. Why? Because the velocity is squared. So what you should see as the radius gets bigger, your velocity also gets bigger, but not at the same rate. Okay? Now, let's talk the last trials, 9 through 12. You're going to keep the same centripetal force. You're going to keep the same radius. But you're going to make the mass get bigger. So as the mass gets bigger, what has to happen to the velocity? It has to get smaller because I want the same centripetal force over here. Okay? So if you look at your data and you can kind of go, wow, this is what should be happening, then look at that. Now, if you look at your data and you have like one point that's completely off the grid, I mean, it's way out there, redo that trial. Okay? Don't go, oh, it's human error, it's experimental error. No, you screwed something up. Okay? Redo that trial. Something went wrong. Okay? Now, the question being, how are you going to get this velocity? Got to have that number. So what can we measure to get the velocity?
K.
The circumference and time. So to get that velocity, you're going to take 2 pi r over t. Now, let's look at what's going to happen in trials 1 through 4. On trials 1 through 4, you're going to keep the radius the same. So are you going to change the circumference?
No.
No. So what's the only way that you can produce a bigger velocity in trials 1 through 4? What has to happen to the value of t? It has to go down. So if you think this through to the next level and go, okay, right, trials 1 through 4, I'm keeping centripetal force, that's going to get bigger. Mass, staying the same. Radius staying the same. So if the only way that velocity can get bigger is if I make the t smaller. So again, when you begin to look at your data, that's what you can begin to look at. Now, down at the bottom of this page, I don't want to see all 12 sets of calculations. All I want to see, very neatly done with all of the correct units, are the calculations for trial 1. Okay? So down here, all I want is trial 1. That's it. Boom. Nothing else. So when you get to page 2, this is where I tell you what I want you to graph. So the first graph, you're going to plot velocity on the x-axis and centripetal force on the y-axis. Boom. There you go. So on question number 2, when I say, using this equation, which variables are held constant, which ones were changed in trials 1 through 4? You have 4 variables: mass, velocity, radius, and centripetal force. So on question number 2, all 4 have to be mentioned. Either they're changing or they're held constant. So when you answer question number 2, you're going to say, hey, these 2 were held constant, these 2 were changed. When you look at the graph, what's the relationship? All I'm looking for on this answer, is it a direct relationship? Is it an inverse relationship? If you really want to get picky and go, oh, well, it's a quadratic relationship, that's cool. Okay? But you don't have to go through and find the value of k and all that good stuff. Now, when you get to question number 4, let me explain how I want question number 4 answered. When you answer question number 4, I want all 4 variables mentioned. I want force, mass, velocity, and radius. So here's how you can answer number 4. You're going to go, okay, since mass and radius are held constant, to produce a bigger centripetal force requires a greater velocity. Something like that. Okay? Or if you don't like that, you can say, well, to create a greater centripetal force with the same mass and radius, that requires a greater velocity. But you want to mention all 4 variables: centripetal force, mass, velocity, radius. So when you answer, listen to me, when you answer questions 4, 8, and 12 on page 2, 4, 8, and 12, you want to make sure that you mention centripetal force, mass, velocity, and radius. All 4 are mentioned. Okay? All 4 are mentioned. Okay. So I'm done. You won't get done with this today because it takes so long to get all this data. Take your time. Do not be afraid to go back and redo a trial. Now, make sure that the rubber stopper is tied on. Okay? Just a word of advice.
I'll make sure of that.
When you look at the tubes, especially if they're glass, usually one side, one end is a little bit smoother than the other. Make sure that's the one that has the string running through it. Okay? I'd start with about 1 meter of string because you can always shorten it, but tough to make it longer. Let me see, other than that, you're on your own. Go be free.